This video presents use case B of the CENTINELA Plus project, a solution designed to predict the electricity consumption of a building 24 hours in advance. The goal is to show how data and artificial intelligence can help manage energy more effectively in educational buildings. In an educational building, electricity consumption is constantly changing. It depends on the time of day, the day of the week, the activity in the building, weekends, and also public holidays. Being able to anticipate that consumption makes it possible to plan energy use more effectively and then detect possible deviations. The final goal of this use case is for the system to look at the consumption history and estimate how much electricity the building will consume 24 hours later. To do this, the system learns from previous consumption values and uses known time-related information such as the hour, the day of the week, or whether it is a public holiday. With this information, it generates an estimate of the expected consumption for the following day. While CENTINELA Plus gathers enough real historical data, we have worked with BDG2, a public dataset containing real building data from different countries. To make the time series coherent, meters from the same region were selected. Then, from that group, the 20 highest quality meters were chosen, avoiding the combination of data that was too different from each other. After cleaning the data, we obtained an hourly time series with just over 17,000 records. In addition to the meter reading, we added variables such as the hour, the day of the week, the month, weekends, and public holidays. This allows the model to interpret consumption within its time context. The system starts from the consumption history and the available time-related variables. Using this data, the model learns patterns and estimates the consumption that will occur 24 hours later. The validation respects the time order. The model is trained with past data and evaluated on later periods. Several approaches were compared: tree-based models, LSTM neural network, a classical statistical model, and a baseline. The baseline is a simple reference, a basic prediction used as a comparison point. In this case, it assumes that consumption at a given moment will be the same as it was 24 hours earlier. This helps us check whether the models actually improve on a simple solution. The main metric was the mean absolute percentage error, or MAPE. This metric shows as a percentage how much the prediction differs from the real consumption on average. The lower the MAPE, the better the result. The best model was random forest with an approximate MAPE of 4.4%. This result clearly improves on the baseline, which had an approximate error of 7.84%. Put simply, random forest produces predictions that are closer to the real consumption than a basic prediction. In addition to comparing models, the result was tested by moving through different periods of the time series rather than using only one final section. This validation helps confirm that the model maintains good performance as time moves forward. The project also ensures traceability through MLflow and LakeFS, registering experiments, models, metrics, and generated artifacts. This makes it possible to know which data and which model produced each result, making the process more controlled and reproducible. When CENTINELA Plus has enough real historical data, this same workflow can be applied to the data captured by the center's sensors. This will make it possible to anticipate high consumption, compare predicted consumption with real consumption, and detect possible deviations. In summary, use case B shows how data and artificial intelligence can support smarter and more sustainable energy management.